it's a big project. A lot of people are involved in it. Yeah.
If the 30-meter telescope is a 30-meter here, then what is the one or the M1 here?
The M1 is, it's called it's the first mirror that the photons hit.
Okay.
And M2 is the second mirror that the protons hit, and so on down the chain.
So could you on this, I'm sorry. I just wonder, scale-wise, on this picture, what is 30 meters?
I'll show it to you, but you can't, this is about 30 meters there, that aperture.
Okay,
It's
thank
just
you.
about a little bit over 30 meters.
Thank you.
So it's, I'll show you some scales of the a telescope next to some buildings in Pasadena, and you can get a sense of how big it is actually. And I used to work, as Rod said, at Keck for 15 years, and started out at the project office in California on the design side of things, and moved out here in '89. I started at Keck in '86, '89 I moved out here, and we normally call this commission, get the telescope built, up, operating, and then I stayed on for the second telescope, the Keck 2, and then through some of the interferometer and the adaptive optics programs, and finally in 2000, for whatever reason, I'm not sure yet, I left. But I'm back in the telescope world, and I'm working for the 30-meter telescope now, which is in Pasadena. The project office is in Pasadena. So this is a piece of a bigger presentation I have. The things I thought I would talk about was, why are you building it? When is it going to be done? Who, where, and how much? Design heritage, and then talk a little bit about the enclosure and facilities, the telescope structure itself, the optics, and then a little bit more time on the controls. By the way, I'm not an astronomer, so I'm going to beg off on any astronomical questions. I pick stuff up. I've been working around it for a long time, but I'm an engineer by training, electrical engineer by training, with an emphasis on control systems. But I think it's important to ask, people say, why are you building this big telescope? And these are the big questions that the astronomers are trying to answer. The nature and composition of the universe, in particular, dark matter and dark energy, which are the terms given to the majority of the universe that we can't see, and we don't understand what it is. But without it, the laws of physics, as we know, don't work. So they ascribe this to dark matter and dark energy. And then the formation of the stars right after the Big Bang, and soon after the galaxies that formed, and then the evolution of those galaxies, and then try to understand how the relationship between the black holes and their galaxies. There's a huge black hole in the center of our own galaxy. Andrea Ghez comes out here and uses the Keck telescopes quite a bit, and she just won some international award. All her work is focused on the black hole in the center of the Milky Way galaxy. And she's actually been able to measure the stars getting stretched as they get eaten up by the black hole. So it's kind of cool stuff. Formation of stars and planets, and then the nature of extrasolar planets. And of course, one of the big questions is presence of life elsewhere. TMT actually has the potential to actually image stars or planets around nearby stars, which is no other instrument presently can actually image. They can detect planets, but they can't actually image them. So if things go to plan, we'll be ready for science operations in 2021, so it's a big, long project. The partners are University of California and Caltech. We're also the partners for Keck, Canada, Japan, India, China. I'm sure hoping that the U.S. government will get into it too, also through the National Science Foundation. But as of yet, they're not partners. They claim to have no money. You know the political situation right now. And it's a costly project. It's $1.3 billion in 2011 dollars, and if you escalate that out, it's going to be quite a bit more as well. It's just a map of all our partners. In fact, when I fly back to Pasadena tonight to LA, and then Sunday morning I got to fly to India, and then I come back, and 3 days later I got to go to Japan. So it's being an international partnership. It's good because it brings all the countries together. It's necessary because any one country or any one organization, it doesn't have $1.3 billion, so you got to collect different partners. But there's difficulties and challenges associated with it. This was a cover page of a proposal that we put into the National Science Foundation. You can just see all the different languages that are down here on the right-hand corner. So So the design heritage is the Keck telescopes on the summit here in Mauna Kea. There are about 7 or so segmented telescopes in the world right now. The 2 that work the best are the ones on top of Mauna Kea right here. Jerry Nelson, Terry Mast, and Gary Channon were kind of the grandfathers of that technology. They were the first telescopes to deal with segmented primary mirrors, and they are the basis for all other designs, segmented telescopes since then. And although there are 8-meter monolithic telescopes, Gemini, Subaru, and others, VLT, once you get above 8 meters, you got to go to segments. You can't build one large mirror. It'll deform too much, it'll break. You just can't do it. So segments as you proceed. And I should say that the Europeans are building a 39-meter segmented mirror, and they have about 1,000 segments. And as I said, the Keck telescopes are extremely successful. What we used on Keck, and we'll probably use on TMT, is something called stress mirror polishing. So all the pieces of the segments are not A-spheres, they're not spherical. Each one in its location, its shape is a little bit different. So that gets really hard to polish. And so Jerry Nelson came up with this idea, how about if you stress the piece, the segment first, in a particular manner, and then polish it like it's a sphere, and let the stress go away and have it bounce back into the right position, right shape. And that's what was used at Keck, and that's what's going to be used on, most likely on TNT as well. So it was a very novel idea, and he explored it, and it took probably a decade or so to mature it.
What's the wavelength correction on that, the tolerance?
On the shape itself,
on the shape itself?
we're looking at, the final shape, you got to look at it in frequency bands, but is, the 50 nanometer type of level. So it's,
Cool. Okay.
now I'll talk about it later, but we actually have on TMT 21 little motors with what we call warping harnesses that can improve the shape, the overall shape of a segment. So there's 21 times 492 of these little motors in there.
So the motors are piezoelectric elements?
These are motors. These are just, you set and forget. I'll talk a little bit more about that.
Are these pieces of glass that you're stressing?
Yes. Yeah, they're low. There's about 3 that's low CTE, so low coefficient of thermal expansion glass. Girodor by Schott, O'Hara by Clear Ceramic by O'Hara. Japan makes it. Corning makes ULE, and the Russians make something too.
What's the total range?
Of the how much we stress it, we can actually move it. It's actually depending on the mode. At a low spatial frequency, it's a micron or so.
There's not a lot of stuff.
Not a lot of stuff. These are edge sensors. I'll talk more about that. We have to align all the segments. We do that with these are Keck legacy equipment, which TMT is based on. This middle one is an alignment and phasing system. Allows us to measure the position of the segments and put it all together so it actually makes a monolithic mirror in effect. And then handling the segments as well. I'll just talk a little bit about the facilities. The site is off the summit. It's actually what we call on the north, down below about 100 meters below the summit, actually, maybe 150 meters. Part of that is for visibility, so it won't be visible. Invisibility, I should say. We've done a whole lot. I was here during the days when it was kind of the perfect storm, when the Keck ran into the master plan for the summit. Was near the end days for that, and so they had to renegotiate that. Keck was trying to put out outrigger telescopes around the 2 big Kecks for interferometry, and I don't know if many of you were around then, but it became a big issue. And there was good reason for it. I don't want to get into politics here, but we've done a whole lot, everything to work on the ground with people, with the politicians, the unions, the Native people, Hawaiian organizations, and trying to make sure that we do everything appropriate and are sensitive to all the cultural issues as well. And that's part of the reasons it's also not on the summit. So headquarters are going to be in Hilo. There's a picture of the top of the summit where TMT will be.
TMP is lower left?
Lower left, yes. And so this is the enclosure design. Three things I want to point out. This is an unusual enclosure for a telescope. There's probably only one other, and it's much smaller built right now. We bought it a lot because of this slant bearing. So the whole enclosure rotates around an axis here, around the bearing at this level. Horizontal bearing rotates. And then this aperture can rotate around this bearing here, around an axis that's this way. And the reason we do that is, one, it's spherical, and so it's economic in terms of the amount of steel that's used. It also allows us to minimize the aperture and match it to the primary mirror, so there's the least amount of wind that can get onto the telescope. And wind shake is a really big issue. So that's one thing. All of these vents can be opened and closed, and that's to get a nice flow of air over the primary mirror, so we reduce the seeing effect. Everything on ground-based astronomy has to do is, how do we see through this fluid we're living, the atmosphere. And so it's like if you're on the bottom of a pool and you look up, and that's the advantage really that space telescopes have. So we do everything we can to improve the seeing. And lastly, these louvers here, flaps, are there to reduce the wind blowing on the top of the telescope. Those are three novel.
Are they?
They just open or closed. I actually have some. So here, this is when they're retracted. In the dark, here is the scale. Okay, so the dark blue, this is how much wind. So red is a lot of wind. Blue is not so much, almost zero wind. And it's all proportional to the outer wind. It's a scale factor to the wind blowing outside. So here, this is without the reflectors. You can see that there's some green even and light blue. This is the top end of the telescope, this little cone-shaped thing here. And so when you put the flaps on, it actually moves the white, actually moves the light blue away from the top of the telescope and reduces the wind shake on the top of the telescope quite a bit. And it doesn't take much because we're trying to, we're trying to keep the telescope jitter down to 50 milliarcseconds. Such a real small amount of wind can be a problem. Yeah.
Do you have adaptive optics to deal with the other atmosphere?
Yeah, we have it's built. It's one of all the what we call there's a term used in the community now called ELT, extremely large telescopes. It's kind of like Monty Python a little bit. I don't know what the next one's going to be. Very, very big telescopes. They're all the Europeans, the one we're building. There's another project in the U.S. called the Giant Magellan Telescope. All of them will have adaptive optics. Without adaptive optics, it doesn't. At some point, so as your aperture gets bigger, your diffraction limit gets smaller and smaller. And that's kind of that's how well you can image. And if at some point, if the diffraction limit gets smaller than what the atmosphere is going to allow you, you're wasting your time collecting more photons. So without adaptive optics, you're kind of wasting the advantage of a big telescope. You can still collect a lot of photons, but you can't get the resolution that you could otherwise.
Can the adaptive optics take into account the flow of air across the face of the telescope, or it's just the upper atmosphere?
There is ground layer adaptive optics, but this yes and no. It's another presentation. So the headquarters are going to be there's at the research park in Hilo. We have a site picked out, the Kumahana site, and we actually have some designs ready for a headquarters. And Keck headquarters are here in Waimea. So just some main characteristics of a telescope. We're going to operate from 0.31 to 28 microns. The emissivity, which is
What's that in? Is that green, blue, red?
it's all the way from UV up to near infrared and a bit beyond. The far infrared is 28. So the emissivity, so it's the radiation of the telescope, which is bad. It's got to be less than 7%. And one of the issues with segmented telescopes is you have gaps, and so you get all this heat that can be thermal that can emit through those gaps. And so we have to keep the gaps very small and overall coat appropriately, so we keep the emissivity down below 7%. The obscuration of the top end, so the photons are coming down. There's a mirror on top. Okay, it has to be supported by something, and we're going to lose photons because of that. And every little bit of obscuration, the astronomers beat the engineers over the head with. And if you think about what it costs, if it's a $1.3 billion dollars for the telescope, and you say, well, you throwing away 4% of the light. That's real money. Same thing with the little gaps. We keep the gaps down at 2.5 meters because again, that's real money. If you get sloppy with that and make it easy, you're going to reduce the effectiveness of the telescope. And, we of course don't want to do that. The field of view is 20 arc minutes. We can observe from 1 degree off of the zenith, pointing straight up all the way down to 65 degrees. We have to point over the whole accessible sky to 1 arc second, and we can track objects up to 1.1 times sidereal rates, where sidereal rates are what you would actually, it's actually the Earth's rotation we're taking at, but what you would see a star move because of Earth's rotation. And we can go 10% higher, so we can track things like comets and things of that nature. And we have to keep our image motions, and this is just the telescope itself, the structure and the optics, so that there's less than 50 milliarc seconds of jitter. At one point I could do it, but we're looking at less than a micron for 2,000 tons telescope in terms of the amount of vibration. And then we have to slew to any other object to another and change an instrument, which is 5 minutes. And again, that's all about efficiency. Astronomers want to make sure everything happens fast and quick. We collect every photon that we possibly can and not give anything up. It's an RC to design, so that, start at the primary. Primary is 30 meters, and F1 with 492 segments. The secondary in its own right is large, almost as big as the CFHT telescope. Primary is 3.1 meters, and it's a convex. That's characteristic of an RC design. And then there's a flat tertiary mirror, which is 2.5 by 3.5 meters. And I'll come back to that in a minute. The overall focal ratio is at 15. Focal surface from the tertiary. So the light path just comes down, hits the primary, bounces off, hits the secondary, comes down, hits the tertiary, the M3, and then it's reflected to the instruments that are located on either this platform or the platform on the other side. Those are known as Naismith platforms. And
How big is the M3?
the M3 is 2.5 by 3.5 meters. And it was an architectural design, early design decision. These instruments are huge. Some of them are about half the size of this room. They just get big with big telescopes. And so we made a decision, in smaller telescopes, you can move the instruments around and get them into the right position. These got too big, so what we said, we're going to keep, these are Naismith platforms, we're going to keep the instruments fixed on these platforms, and we're going to use the tertiary, the M3, to move the beam of light to that instrument. But that means it has to track just like a telescope, so it's always moving and it has to maintain that optical beam onto that instrument. But the advantage, of course, is you can put more instruments and you don't have to move them, or you don't have to put another mirror reflection in there in order to put the light onto the instrument. So I mentioned all of this about the instrumentation. There is an azimuth, so this rotates about an axis this way, we call that azimuth. And then there's another axis this way. So the whole thing tilts like this, and we call that the elevation axis. We're using linear motors, so actually the azimuth motor is 34 meters in diameter. And it's made up of rare earth magnets, sections that we put together. And so it's just one large motor. Gives you the best performance. There's no gears, there's no pinions, it's just a direct drive motor. And the elevation motor is around these rockers, and it's about 10 meters in. It's actually 10 meters in radius, so it's 20 meters in diameter.
What's the bearing?
How many horsepower?
I don't actually know. I don't have that at the top of my. I know it in. There's over. I know in torque. There's over a million Newton meters of torque capability. Somebody asked about the bearings, or
Yeah, I was just, is it,
the oil bearings.
Palomar was on wheels or something, but now it's.
Yeah, Palomar was the first telescope to use hydrostatic oil bearings, and so it's high pressure oil, gets down, flows through a pad, and then there's about a 50 micron or so gap that lifts the telescope. And we'll have the same thing. We'll have a hydrostatic bearing. They're out at this outer radius, and also on these rockers for elevation and azimuth. The And then in the center, there's a pintle bearing that keeps the telescope centered.
To no mercury.
No mercury, no, not at all. At Keck, and it'll be the same thing here, you need all that torque, that million Newton meters of torque, so that you can accelerate this telescope and move to a different object. But when you're tracking an object, the acceleration is almost zero, the speed is very low. The oil hydrostatic bearing is almost frictionless. So at Keck, if you took, there was 8 drive motors out at about 8 meters radius, 60 meters, and if I took a heavy-duty torque wrench, plugged it in, dropped it onto the end of the axle of the motor, just had it tilted a little bit, so there's a little bit of a moment, it would move the telescope. It just the weight of that torque wrench would just slowly go down, and the telescope would move if it was on oil. So we do a lot of finite element modeling, where the dynamics of the telescope are really important. Just to say that the structure has about 35,000 elements in it, in the model, and 20,000 nodes, and 120,000 degrees of freedom. And most of those, the vast majority, are inside this mirror cell itself. That's where most of the complexity is, or a lot of the complexity. I have an AVI, but maybe I'll see if I can, just to show one of the modes. So there's an FEA, and it's just showing it's one of the low frequency modes. This is at 2.5 hertz, and it's the rocking of the whole tube on it. And these are the type of an analysis that the mechanical and structural engineers do in order to optimize the telescope and make sure that we can control it.
So Mark, what is this showing?
So this is just showing if you, every structure has a number of different modes that it will naturally vibrate at or resonate at. And so this mode here, you can see the tube is rocking back and forth this way. And we're mainly interested in the very low frequency modes. This one is at 2.5 hertz. And so it interacts with the control systems. So we always want to make it, we would love to have all those modes stiffer, meaning higher frequency, but that costs, it's 2 things. It's more mass, it's more steel, and at some point with more mass pushes the frequency lower, but it does get stiffer, and so it's kind of a diminishing returns. And what happens if you don't have a stiff telescope, you can't control it well enough, and so then it kind of shakes in the wind, or a lot of things can cause it to shake. So. And that's just one. There are thousands of modes. We worry about maybe a couple hundred of them.
So do you have active compensation against the vibration?
We don't have, we're not using smart structures, if that's what you're asking. Let's skip through this. This just talks about the different masses. So am I going at the right speed? Should I move quicker? Is this okay? Okay. So this is the mirror cell that I was talking about, and I'm very much involved with this because these little hexagons up here are the 492 segments of the primary. And so you can see there's the upper layer of the cell is highly, it's very dense, and it gets a little more dense here. This is the mirror cell floor, and this right here is the floor, and when you walk out to maintain or do something to one of the segments, you walk on that floor, and the mirror is above you. And then this is the lower part of the tube, and it's the dynamics. What makes this difficult, one of the big challenges with controlling the M1, is that what you do over here to one segment gets seen by another segment over here. And so if you imagine for a moment that you had a 30-meter waterbed and you had 3 people and 492 segments, and you all were trying to hold them up and align them, and somebody's moving over here, it puts ripples all the way through the waterbed. And this is happening all the time, and so it's called control structure interaction. It's the interaction between all those pieces which make the control of the M1 difficult. At Keck had 36 segments, so it was a lot smaller. But the other thing is, because it was smaller, we weren't so worried about the wind. It wasn't as big of a sail. 30 meters, it becomes more of a sail, the wind forces are greater on it, and we're trying to do better. So we have to have higher bandwidth. In other words, we have to make it stiffer over a range of frequencies by a factor of 10 or so than what Keck had to achieve. So that's one of the big challenges here with TNT. I'll talk more about that. This is just some dimensions. So top of the enclosure is 56 meters. And the elevation axis is 23 meters, and then there's platforms over here for the instruments, and those are 17 meters. And so these platforms, well, right here, this is, it's a half a football field, more than that. And so it's a large, big, and it's tightly wrapped around the telescope. We tried to keep it as small as possible. This is the building that I work in Pasadena. It's a 6-story building. If you put the telescope behind it, then it's about twice as high and about the same width. So every once in a while, I look at this and I start shaking my head. I go, we're crazy. What are we trying to do? I'll go to the optics. So now we start talking about the primary mirror. There's mass, the overall mass. There's 492 hexagonal segments. The mass of the whole mass of the M1 is 131 tons. 75 tons of it is glass, and they're only 45 millimeters thick each all the segments. 56 tons of it is support structure. And then there are 6 identical sectors that make up, and there are 82 segments in each sector. And each segment, each one of those 82 segments is a little bit different, because if you project a hexagon and you want to keep the gaps the same, each hexagon is a little bit different. So there are 82, there are 6, so there's 82 different segments, shape segments, just a little bit different, and then it's repeated 6 times.
So roughly how big is a segment?
It's 1.4 meters from corner to vertex across it. And then the other thing is the asphericity, which is how far off of a sphere, ranges from 6 microns to 226. And the mirror, by the time you get out to the outer side, the perimeter of the mirror, the slope of that out there is 15 degrees. So it's pretty high slope already by that time. So it's a big dish. Another thing, it's very fast. Camera speak. In other words, it's an F1, and then what that does is keeps the height of the telescope shorter. Otherwise, you get very long, and you have a bigger enclosure and more steel and everything. So that makes the optics very fast.
Would you mind putting your hands like it's approximating is it like this or like this? The shape of the
Oh, the shape?
Is
The
it
shape,
almost flat?
yeah, the outer, it's a good thing. It's maybe a quarter of a millimeter.
That's what I'm thinking.
Yeah, it's just each one is just a little bit, but then it adds up as you go out. But if you looked at any one segment, you'd have to really look to see the asphericity.
How do you control the dithering again? When the telescope is moving, vibrations?
On the mirror,
each segment.
on the segments. Just give me a second, I'll get to that.
Sorry.
And so there's also 82 spare segments, so that we can take segments out, replace it with one of the spares, and have that recoded. And we recode segments. With the coatings we have today, we got to do it about every 2 years. We're hoping if we get durable coatings that we can make it every 5 years. But if you start, it's the same thing. If you start losing reflectivity on your segments, you're throwing away light, and you're throwing away money, and you get your astronomers really pissed at you really quick.
Can you suffer the loss of X number of segments, still operate, or?
Yeah, yeah. There are some science programs that's not really good for, but other science programs you can.
What is X?
Huh?
So what is X?
Oh,
is it
X.
small or is it big? Is it 1 or 100?
It degrades. I mean, nothing says you couldn't operate with 100 segments out, but you're going to get a lot of diffraction patterns and a lot of noise in your imaging. So it's not, at some point, it's not worth it. But you could, 1 or 2 for most programs would be fine. If you're doing something that is, we have what's called a climate finder. It's very edge sensitive to the edges and the diffraction patterns. Then you want all of them in there. Again, did you?
What's the main reason you lose reflectivity, and what do you do to repair it?
But You just lose it because the coatings get dirty and they get worn out and so on.
Just wash it.
And then you take them out, well, we wash them in situ there, but we take them out and we have a coating chamber and we recoat them. So it's a silver coating that we put on it. And so we strip the old coating and put down a new coating.
You get tarnished? So,
There's an overcoat on it. There's a lot of work that goes in coatings, and because you got to get the reflection over the full range. You have 0.31 out to 28 microns, so there's only certain coatings that will work. And
why not gold or aluminum?
well, we do Keck uses aluminum, but it doesn't give you the frequency range as well as you would like. I think it falls off both in the UV and at the higher end of the infrared. I'm not sure.
I thought gold is the
Gold
standard.
gold
for
is
infrared.
standard, but that's a little bit pricey.
So what would be, how would you get to 5 years instead of 2? What would be the difference?
I'm not a coating. It's just there are coatings that will last longer and more durable than
It'd be
others.
something on top of the silver, probably.
It could be something on top of the silver. It could be that doesn't change the reflectivity. Trying mechanisms that allow us to keep the segments cleaner would help also. It's difficult to actually clean them as well as you might like in the telescope.
I didn't quite hear what you said about the aluminum. Did you say that it didn't reflect the IR so much?
I know that it doesn't have the full reflective range that we need from 0.31 to 28. I think it falls off at the UV at the low end. I'm not sure about the high end. It might have somebody else out here as a physicist or something might know. And I know Keck uses silver. And Gemini, on the other hand, uses a silver coating. And Keck had a infrared secondary. It's not used anymore, but it was gold coated. But if you start putting the gold on all of these segments, and then you still have to recoat them every so often, it gets to be an expensive process.
2.4 billion.
Yeah.
You know what
Every
Canada
2
France-
years.
You know what Canada France uses?
I think they use an aluminum.
Aluminum, yeah, they have an aluminum facility.
This is a nice picture.
Yeah. There's 45 millimeters thick. There's 2.5 millimeters gap between each of the segments. That cost us 0.6% of loss collecting area. The astronomers would like us to even make the gap smaller, but at some point we just have to say, can't do it. So the segment supports, so every segment has a support structure. And there's 6 degrees of freedom that any segment can move in. 3 of them are constrained passively by the segment support structure. So anything that's in plane, so X or Y motion in plane or rotation in plane is controlled by mechanics. And then the other 3, which is tip and tilt and piston, is controlled by the active control system, which I'll talk about in a moment.
45 millimeters thick, what's the back look like?
It's a meniscus, so it's 45 millimeters all the way across. The Europeans, for whatever reason, they're building a flat back, so
Okay.
but we're not. So
Still.
It's good skinny.
it is. Keck segments are 1.8 meters, and there are 75 millimeters thick. We're pushing the aspect ratio quite a bit, and so the support structure has to be really.
Yeah, really good.
So I talked about this. Okay, and here are there's 21 degrees of freedom with warping harnesses, so there's 21 little levers that can change the shape of the mirror. But we only do that once every 2 weeks or whenever we put a new segment in, we measure the shape, we adjust it, and then we leave it alone. But that's the baseline plan. So it's not active in that sense, it's a very slow control loop.
How long is it to replace the segment?
So we wanted to, actually, good question, because we're shooting to be able to do 10 in a day. Keck does 3 in a day. But with that many segments, if we have to change them every 2 years, that means every 10 days we're changing, or every 2 weeks we're changing 10 segments. And if it takes a whole day, that's a whole day out of the day, during daytime operations to handle that operation, to do that, which means something else isn't getting attention that might need it. And so it's expensive, and that's why what's good about, there's 2 things we do. One is we want to get durable coatings, so they last longer, we don't have to change them as often. The other is that we've worked really hard to make the segment exchange process very efficient.
My fast, it's still all just design phase, right? Nothing exists yet.
There's prototypes that exist. and quite a few different prototypes of things, so we're on the design phase still. But some of the things I'm talking about are, I mean, it's kind of funny to think of Keck as a test bed or a feasibility study, but, you know, the fact that Keck works so successfully gives us a lot of confidence, and our sponsors a lot of confidence that TMT can be made to work as well. That's okay. Yeah.
How do you measure the shape in situ when you install?
Using Starlight with
Okay.
with Shaq Hartman.
Okay. Very cool.
This is just the process, again, I mentioned, stress mirror polishing. And then it's cut into a hex and mounted onto back the segment support structure. And then there's something called IBF, ion beam figuring, where you can actually run it through a machine and it actually takes out the last layer, because kind of like a fine polish. And we did that at Keck. Initially, we weren't doing that, and we weren't getting to the surface characteristics that we need. So now it's kind of a baseline. So this is the what's called a mounted segment assembly. So there's 492 of these assembled. So starting from the top, this is the segment here. It's 45. It's a hexagon, 45 millimeters thick. These are edge sensors, and there's two. An edge sensor is made of two pieces. So there's an adjacent segment with another piece like this. So there's two. A sensor with one flat here and one flat here. The capacitive. And so between every inter-segment edge, there's two sensors. So for a segment that's in the middle of the array, there's 12 halves on it. So it's 6 times 2. This here, and then there are dust boots around it as well, and we also purge it with dry nitrogen to keep the humidity down inside by the sensor, because the capacitive sensors are humidity sensitive.
Why?
We could use dry air too. It's just dry gas. The support structure is called a whiffle tree. You can see these thin rods coming up. There's 27 of them, so there's 27 points
Per
support
Per segment?
per segment, yeah, that support in a kinematic fashion, support in an axial direction, support the segment with minimal deformation of the shape. So it's so thin, and if you just support it, let's say at 6 places, it would bend. And we're trying to hold it, we're talking at the nanometer, or 10s or 20s or 100 nanometer level. So you got to support it just right so it doesn't bend at all. It doesn't deform, so the shape that you polish remains. And then inside this, and then when there's, so a segment, that's what supports it when it's looking straight up, and when it goes over this way, now the forces are different. They're not axial, but they're lateral. And that's done by this tower. They're inside on the back, inside the segment, in the segment, there's a diaphragm that's a board, a whole-lunch board diaphragm. A diaphragm's put in, and that provides the lateral stiffness. And then there's a secondary offload within this blue tower, because we have to move this up and down. It has a 5 millimeter range. And if the diaphragm inside, if we were putting 5 millimeters in that pancake diaphragm in the segment, it would deform the segment. It would print through the segment. And this is much more difficult than Keck. Keck only had 1.2 meters of range. We have to do 5 meters because the structure is so much bigger and it bends so much more. It's just heavier, it's bigger, it bends more. This right here is part of the upper mirror cell. So this is part of the structure, this white piece here. And then these are the actuators, and they're attached. It looks like they're attached to the mirror cell, but it's actually attached to what's called a fixed frame, the silver parts that's inside this white structure. And so when we pull the actuators in this fixed frame, once they're installed, surveyed, installed, adjusted, they stay in the telescope. And when we pull out a segment, everything from the bottom of the blue on up comes out of the telescope. Everything else stays in the telescope. And the actuators attach, there's an output shaft here, and it attaches to this gold piece, this upper gold piece, and moves that in such a way that you can tip, tilt, and piston the segment. The secondary is 3.1 meters. It's 100 millimeters thick, and it's a hexapod that does the positioning on that. And the tertiary is 2.5 by 3.5 meters. I mentioned that before, 100 millimeters thick, and it's on a positioner assembly that allows it to rotate again about an axis this way. So it can rotate about this bearing here, and also about this one, so it tilts. And you need that motion as you keep the optical beam going into an instrument that's off axis. You need that articulated motion, so it's continually moving very slow but very precisely to keep the beam going in the right place. So I'm going to talk about M1 control, and probably all the time that we have. So the M1CS, which is the M1 control system, along with the alignment and phasing system, turns a bunch of segments into a monolithic pair. And so the way we break it up, the M1CS keeps the shape of the primary despite changes in gravity. So when you move the telescope from horizon to zenith, the mirror has a tendency to sag and deform, and so it makes sure that that shape, the right shape, is maintained. It also attenuates temperature against temperature changes, wind forces, and vibration. But where the M1CS keeps all the segments is determined by the alignment and phasing system, and called align and phase, and that's done using starlight, either once every 4 weeks or whenever we put a new segment into it. Because when we put a new segment in, we have to recalibrate the sensors, and we use starlight to do it. If we don't put a new segment in, let's say for whatever reason, the system should work fine for 4 weeks. It slowly will drift out of spec, but our spec is to be able to maintain it over 4 weeks. And so the global M1CS controls the global shape of the M1, so the overall shape of the M1, and it uses edge sensors and actuators. And then we have what's called a real-time acquisition and guide and wavefront sensor that's used continually while you're observing a science object. It takes a little bit of the light, it can measure the shape of the primary, and those adjustments are then fed back into the primary, and it also can be fed back into the secondary to keep the focus right and the collimation right so that everything stays aligned. Or it can use an adaptive optics system. Somebody had mentioned that, which is it takes out the atmosphere. And the difference there is that the adaptive optics system only has limited range. And so as it begins, those corrections build up over time, and it will saturate the deformable mirrors or the wavefront sensors, and then we offload it. We take those errors and we say, push that correction onto the telescope.
What's the update rate?
Well, there's different. I mean, there's a guider feedback for the acquisition, which is maybe 1 hertz, and then so everything that goes off of the on-instrument wavefront sensor is probably 10 hertz and slower to the telescope. The adaptive optics system is working much faster. So here's a picture of a real simulation. So this shows you, imagine the red being segments that are being rattled around by wind, okay? And the number we call it optical path difference, but just think of it as the shape of the primary. Here at the RMS, the average optical path difference is 110 nanometers. That's what the M1 control system turned off. You flip the switch, and it turns into that. And then it's only 29 nanometers, so it reduces it by just making it stiffer against the wind disturbance. I won't go too far in here, but the actual math associated behind this isn't that difficult. It's a lot of it, but it's not, and it comes down to that the sensor signal, any one sensor, is a function of that actuator business. So this sensor signal is a function of these 3 actuator lengths and those 3 actuator lengths. And if you duplicate that, there are almost 3,000 sensors. You end up with this big array, and you do the equations of correction out of using that. So it's not, there's a lot of details that go into it, but the basic concept isn't that difficult. The sensors measure the height between 2 segments, which is important. But the other thing it also has to measure is what we call the dihedral angle, because the height could be correct, but the angle could be wrong. And we call that focus mode. And so the sensors have to have the capability to measure that height and also the dihedral angle. It's just a block diagram showing the electronics and sensors of the game. So on the actuator side of things, we have to build actuators that starting off with K, that had 1.2 millimeters of range and about, a few nanometers of resolution. It's about the same for TMT, but our range had to be 5 millimeters. Same resolution, 5 nanometers is what our resolution needs to be here too. But they had to be a lot cheaper, and they had to be much more reliable. So we had a whole prototype technology development effort. This was a fluid-driven piezo actuator. This was a JPL hard actuator using piezos. This was a soft actuator. I guess I should have. Soft actuator you can think of using a speaker, a voice coil, where a hard actuator is like a screw or a piezo. So soft actuator, if you don't control it, it's just soft. There's no holding force. A hard actuator, you turn off a screw or a piezo, it's still stiff. And so we tried both types, and there's reasons we chose one over the other. Anyhow, we ended up with this. This is without covers, but that's our present actuator on the far right. Actually it looks complicated, but it's pretty simple. There's a 4-bar linkage with a voice coil for fine motion, and then there is, because it's a soft actuator, you always need to power it, and so there's a lot of power and heat going into the system. And so we had to take that, use an offloader to offload the weight of the segments, the DC, the average weight of the segment, in a way that is with minimal power, so it doesn't put out a lot of heat, which is bad for the observing. And then likewise, this was a Keck sensor, and we ended up with these cap sensors. So Keck sensors were done; they were interlocking, and they were big and expensive. And every time you change a segment, you had to swing things out like that. So now we're just using 2 pieces of glass. These are gold-coated glass, and we're using out-of-phase signals on these 2 drive electrodes, and then the capacitance between that and the sense electrode gives you the height difference. So if everything's aligned and they're out of phase, you get 0 charge in effect. And as you move them relative to one another, differential, you're overlapping one electrode more than the other, and that's what gives you the difference in capacitance and gives you a height signal. I'm going to go past this. Yeah, so the other thing we do here is on the back of the this is just a coupon of glass. We actually put pockets in to very high tolerances, because the sensors have to be mounted with reasonably high tolerance. Otherwise, as they move relative to another, there's motions of the segments as you change gravity or temperature, that they slide relative to one another. Not a lot, but hundreds of microns. And if the sensors aren't perfectly installed and they're, let's say, a little crooked like this, as they slide, it interprets that sliding as a height signal, and you get it's cross-coupling. And so there is a combination of, and on the other hand, we couldn't put them in perfect, it would cost too much. And that's what actually got us back to this. We came up with a really unique calibration algorithm. And this says, I'll get to it in a minute. And this is just jigs for installing the sensors. No, I don't have it anyhow. The point was, with the calibration algorithm, it loosened how the tolerances were needed to install the sensors in, and allowed us to achieve the performance we needed as well. So it was a way of using, being smart about the calibration that allowed us to be a little bit sloppier in the installation. And these are the types of PSSN is just a metric, and that's it over here. And a perfect telescope would be 1. And we're supposed to produce a telescope that is 0.85, so we're going to lose 15% due to just the all the different error sources on the telescope, ignoring the atmosphere. And so this is just saying these sensors, the error to the sensors, this is temperature. We have to operate over from 6 degrees to -4 degrees. So that's temperature over here. And this is the angle that we have to operate over. And this is with, if we do an APS run, which I didn't do, but that's using the sky to calibrate. And if we only use one, you don't do a good job calibrating. A lot of it is pretty, you get PSSNs over this whole range, and a lot of 0.1, we can't use it. And as we use more runs, more calibration on the sky, things get better and better. This just talks about the electronics on the back. I think the only point here is that this is a listing of all the different electronics components and how many there are. So there's thousands of assemblies on the back of the mirror to control the mirror. And over here